At the deepest hardware level, a hard disk stores information as tiny, distinct magnetic regions. Each bit of binary data, every 0 and 1, is physically represented by the direction of its magnetization, pointing either up or down. For decades, the primary method for increasing a drive's capacity under perpendicular magnetic recording, or PMR, has been a simple geometry problem: fit more bits into the same physical footprint. To pack more terabytes onto a single platter, engineers have to physically shrink the volume of these individual magnetic grains and pack them closer together. Shrinking grains to this scale triggers a catastrophic failure mechanism at the quantum level. The quest for higher areal density has slammed into a strict physical limit, where the laws of thermodynamics actively erase our data. This diagram illustrates the foundational problem of modern data storage, known as the magnetic recording trilemma. At the top, we have the requirement for small grains. This is the non-negotiable physical prerequisite for increasing storage capacity. On the bottom left is thermal stability. For a drive to be useful, the data written to it must survive ambient room temperature heat without that thermal energy causing the bits to randomly flip and corrupt the data. On the bottom right is writability. The material must be responsive enough that the magnetic field generated by the write head can actually flip the bit state to record information. The core paradox is represented by the fractured connection at the base. You cannot achieve all three simultaneously. Shrinking grains destroys thermal stability. Increasing stability destroys writability. Heat-assisted magnetic recording, or HAMR, does not compromise on this trilemma. It bypasses it entirely. By turning a static quantum limit into a dynamic, temperature-dependent cycle, HAMR allows engineers to isolate these inherently conflicting requirements. This graph represents the energy barrier that protects a bit of data. The height of this barrier, delta E, is determined by multiplying the material's magnetic anisotropy, Ku, by the physical volume of the grain, V. At room temperature, random thermal energy acts like a constant vibration, shaking the magnetic state. For long-term data storage, the energy barrier delta E must remain massively larger than this ambient thermal noise. Otherwise, the vibration pushes the state over the peak, and the bit randomly flips. As we shrink the volume of the grain to increase capacity, the height of the energy barrier drops in direct proportion. The consequence of this lowered barrier is modeled by the Neal-Arrhenius law, which calculates the average time before a spontaneous thermal flip occurs. Because the relationship in this law is exponential, a tiny drop in grain volume causes a massive decrease in data lifetime. What was stable for decades evaporates in a fraction of a second. This is the superparamagnetic limit. Without changing the material itself, shrinking magnetic grains guarantees data destruction. The mathematical fix is straightforward. If the volume must decrease, the magnetocrystalline anisotropy, Ku, must increase proportionally to maintain the height of the barrier. This requires new quantum-engineered materials. One critical candidate is chemically ordered L10 iron platinum. This specific crystalline structure uses intense spin-orbit coupling from the platinum atoms to create immense perpendicular anisotropy. Iron platinum successfully secures thermal stability. It allows for microscopic, high-capacity grains that will not spontaneously flip at room temperature. But the side effect is fatal, as defined by the anisotropy field equation. Because the material possesses such a massive Ku, it strongly resists being switched by external forces. The magnetic field acquired to rewrite this highly stable iron-platinum grain is now significantly stronger than the field any physical write head can generate at room temperature. Engineers successfully created the perfect storage medium, but it is so stable that it is functionally impossible to write data to it. Since we cannot increase the magnetic power of the write head past known material limits, we must temporarily alter the quantum physics of the storage medium. This requires applying heat precisely to a single nanoscale bit. Because a normal laser is limited by optical diffraction, it cannot focus tightly enough without heating the surrounding data. Instead, HAMR utilizes a near-field transducer. It takes incoming laser light and uses localized surface plasmonic excitation to compress that electromagnetic energy into a nanoscale optical hotspot directly on the target grain. The goal is to rapidly heat the grain toward its Curie temperature. This is the specific thermal threshold, where thermal disorder completely overrides the quantum exchange coupling holding the atomic spins together. Look at the formal magnetic free energy equations here. During the HAMR right cycle, the variables are suddenly altered by temperature. As the material hits the Curie temperature, its temperature-dependent anisotropy and coercivity plummet. The massive energy barrier that protected the data at room temperature is temporarily flattened. The iron platinum becomes soft and highly compliant. Heat is not storing the data. Heat is a quantum softening tool that opens a brief thermodynamic window where writing becomes physically possible. In the exact millisecond the grain is hot and magnetically soft, the right head applies its standard magnetic field. This applied field biases the Zeeman energy of the region. It forces the chaotic, fluctuating quantum spins to favor alignment with the desired bit direction, choosing either a 0 or a 1. But writing the state is only half the battle. The bit must survive the cooling process. A HAMR disk is not a single magnetic layer. It is a complex material stack. Beneath the recording media sits a highly specialized heat sink layer. The instant the near-field transducer passes, this sink rapidly draws the thermal energy away from the magnetic grain. This initiates a violent quenching effect. As the temperature drops, the material's anisotropy violently rises back to its massive room temperature state. The final magnetic orientation is now locked securely behind an insurmountable energy barrier, completely immune to ambient thermal fluctuations. Executing this cycle at the Curie temperature introduces a highly volatile state dominated by thermal spin fluctuations, creating extreme engineering tolerances. This section on backswitching details the primary error mode, the intense competition between Zeeman energy and thermal energy. If the right field does not sufficiently bias the cooling grain, ambient thermal energy can cause the bit to randomly flip back before the energy barrier hardens. To prevent this, and to avoid erasing adjacent bits, the system must perfectly balance the optical spot size, the thermal gradient, and the exact nanosecond rate of cooling. Compared to conventional perpendicular magnetic recording, which operates almost entirely through magnetic fields, HAM requires manipulating nanoscale materials at high speeds. A modern HAM drive is a mass-produced application of atomistic spin dynamics and nanophotonics, engineered to maintain 36 terabyte stability by precisely controlling the thermal phase.